Tomorrow it is crystalline Dieudonné theory. In particular, I want to explain a proof of the Serre-Tate theorem and of the other theorem that Ching Li referred to, sometimes referred to as growth-antique messing. So the first thing I want to do is indicate I gave a Bourbaki talk in June, Travaux de Zinc, and there's a bibliography. This is available, the entire expose is available on the Bourbaki website, so if you have any interest, you can download a copy. But if you go to the second page now, thank you. So there, could you go back down, please, again? I want page 22. So you can see some of the references that exist in the subject. In particular, for today's talk, there are the 6 references to zinc, and there's a quite recent, that is mid-July, paper on his homepage, joint with Langer, which discusses so-called higher displays. I am not going to talk at all about higher displays. So I want to now, if we go to the second PDF file, I should say there's something ironic in my using this technology. I am the world's biggest Luddite. And despite that, we have this technology. So formal groups were introduced by Bachner back in 1946 in a paper in the Annals, and I'll take 10 seconds to tell an anecdote about Bachner. At Princeton, you're required to have foreign language exams, and one of the exams for me was German, and those who have spoken to me or heard my attempt to speak German, my one sentence is Schnee ist weiß. Know that, and anyone who encountered Bachner would know that he gave the German examination. He had very, very little patience for these graduate students, perhaps good in mathematics, but terrible in German. So he would ask somebody to read a page from some mathematical text. In my case, it was a book by Bieberbach, and he stopped me because he just couldn't tolerate the way I was pronouncing German and destroying the language of his song at his cradle, as Hermann Weyl would say. And I now go on. Formal groups, probably or possibly everyone here knows what they are, but if we have a Q algebra R, the category of formal groups is equivalent to the category of Lie algebras over R. By the funct attaching to a formal group, it's Lie algebra. This is completely false in non-zero characteristic or over the integers. And Dieudonné, following Chevalley, realized just how false it was and wrote a series of 15 papers between 1952 and 1958 where he created what is called Dieudonné theory and Zink's theory of displays, Cartier's theory of typical curves. These are all crystalline theory, all variants on the original theory of Dieudonné, which very few people read his papers these days. They've been in some sense superseded, although not entirely, as I'll come to in the second half of the talk with the handwritten transparencies. So let's go to the second page. So I want to review for you a way of thinking about formal groups. There are many ways. We consider for R a commutative ring the category of nilpotent R algebras. That is, algebras, now there's a misprint. There exists a little n such that the script n to the power little n equals 0. That is, it's nilpotent as an algebra. Any R module is regarded as a nilpotent algebra simply by assuming that its square is 0. And a formal group now is a functor from the nilpotent algebras to abelian groups. There's no reason for them to be abelian except Dieudonné theory concerns itself with abelian commutative formal groups. And in the second half of the talk, I'll talk about an idea due to Grothendieck for classifying non-commutative formal groups, an idea which unfortunately was, as far as I know, never really worked out, and the idea was never published. So can we go to the third transparency? So this functor from nilpotent algebras to commutative groups is supposed to take short exact sequences of algebras, that is, each is an algebra, but its short exact sequence, a sequence of modules, into a short exact sequence. It's supposed to, if the MI are modules regarded as algebras of square 0, it's supposed to commute with direct sums. And finally, R thought of as having square 0, G of R is supposed to be a finitely generated projective module. So we can go to the third transparency now. And so an example is if we take the formal multiplicative group, the explicit law is, of course, 1 plus x times 1 plus y is 1 plus x plus y plus xy. If we have an abelian scheme, then its formal completion at the ident of dimension G, its formal completion is a G-dimensional formal group. If G of R is free of rank R, then G is isomorphic to the formal spectrum of a power series ring, and we get the classical notion of a formal group law as defined in Bachner's paper. G is P divisible provided if we take the multiplication by P, which corresponds to n power series in 2n variables, in n variables, each xi is nilpotent in the power series ring modulo the ideal generated by these, and this implies, by a version of the Weierstrass preparation theorem, that in fact this ring is finitely generated and projective as an R module. So we can go to the next transparency. So I want to if we have a P-divisible group, then as opposed to Franz's lecture this morning, I'm not going to assume that R is spec of R is connected, so the height function is a locally constant natural number valued function. And I mean, there are interesting examples of big products of rings where one can have spectrum totally disconnected. An example I want to look at for a moment is if we take the so-called Lubin-Tate groups, if we take K over QP, a totally ramified extension of degree E, the ramification index, and pi, we fix a uniformizing parameter. If phi is a power series in the ring of integers, coefficients in the ring of integers, and phi of t is congruent to pi times t modulo terms of degree 2, and phi of t is congruent to t to the p mod pi, then there is a one-dimensional formal group, Lubin-Tate group, such that phi, thought of as this power series, induces a lifting of Frobenius on the reduction of this formal group modulo p. And we'll come back when we talk about displays to explaining explicitly what the display associated to the Lubin-Tate group is. So if we can go to the next transparency. So here I review, but we'll skip it because it was gone over already this morning, the definition of a p-divisible group, which is not necessarily a p-divisible formal group, not necessarily connected fibers. And finally, again, if we have a g-dimensional abelian scheme, the kernels of p to the n define a p-divisible group of height 2g. So Dieudonné theory is supposed to classify via linear or semi-linear algebra, more precisely, p-divisible groups. And it depends upon the context how the classification goes, but I think we can go to the next transparency. So I want to begin by reviewing the Witt vectors, which is necessary in order to talk about what displays are. So we have a functor from commutative rings to commutative rings. Explicitly determined, we have the so-called ghost component, composant fantôme in French. Wn of x is x0 to the p to the n plus p times x1 to the p to the n minus 1 plus etc. plus p to the n times xn. And there are two maps, little f from w of r to w of r. So the characterization is that each w of n, w sub n, each ghost component should be a ring homomorphism map. And this determines uniquely the ring structure on w of r. If p is invertible in r, then w of r is naturally isomorphic via these ghost components to the countable product indexed by the natural numbers, r to the bold n. So there are two endomorphisms, Frobenius and Verschiebung. F is a ring homomorphism. V is only additive. So the note, etc., should be below this, but I go now. F is characterized by the nth ghost component composed with F is the n plus first ghost component, and V is characterized by the nth ghost component composed with V is 0 for n equals 0, and is P times the n minus first ghost component if n is at least 1. We can go, well, let me just note before we go to the next transparency that the definition of a ring structure on W of R doesn't require that R have a unit. W of n for n in nilpotent algebra will be a ring without unit. Of course, W of R is a ring with unit, commutative ring with unit. If R has, we can go to the next transparency. So let me immediately remark for use a little later that first, if R has characteristic P, then Frobenius is just induced by, that is, little f is induced by Frobenius on R. It's, W of R is a functor. Always one has f applied to little x is congruent to x to the p modulo p, so that the little f lifts Frobenius on the ring W of R mod P times W of R. We set I sub R equal the kernel of the ghost component map, which sends a Witt vector to its 0th component. And note that this is trivially the image of V. Finally, if R is a Z localized at P algebra, the ideal IR has a divided power structure, so-called canonical divided powers. The nth divided power of V of x is p to the n minus 1 over n factorial, which is an element of Z localized at P. times v of x to the n. If m and n are any two w of r modules, an f semilinear map is a map which is semilinear with respect to f. If we denote by m upper 1 in parentheses the extension of scalars using little f, we'll denote by u natural the linear map from m upper 1 to n corresponding to the semilinear map u from m to n. From now on, assume P is nilpotent in the ring R, or at least topologically nilpotent. We can go to the next transparency. So I want to introduce the notion of a display, Zink's notion of a display. It consists of, it's a quadruple consisting of a finitely generated projective W of R module P. It's referred to as a display over R, but all structures live over W of R. Q is a submodule. F goes from P to itself, and F1 goes from Q to P. These are both little f semilinear maps. And then there are the three axioms. The first axiom is that IR times P is contained in Q, and P modulo Q is a projective R module. So the sequence Q modulo IR times P goes to P modulo IR times P, goes to P modulo Q, will therefore split, and that will correspond to the Hodge filtration that we've discussed earlier. The second is that the F1 natural from Q upper 1 to P should be onto. That is, F1 of Q should generate P as a W of R module. And now the third condition is that F1 of V of C times X is C times F of X for C in W of R and X in P. And if we take C to be equal to 1, we see that the giving of F is in fact redundant. F1 will determine what F is, but in fact it is necessary to impose condition 3 in order to get anywhere. So there's an obvious sense in which there's a notion of morphism of displays. Displays form not an abelian category, but an exact category. That is, there's a notion of an admissible monomorphism, an admissible epimorphism that I don't need today. So I refer you to the Bourbaki talk for the exact definition. We can go to the next transparency, or next slide now. I want to give some examples of displays. Well, excuse me, it's here. I didn't finish that one. The display associated to the formal multiplicative group has the quadruple W of R, I sub R, F, and V inverse going from I sub R to W of R. If R is a perfect field of characteristic P, more generally, a perfect ring of characteristic P would do, but let's take the case of a field, then M goes to P sub M, where P sub M is the quadruple M, V of M, F and V inverse, gives an equivalence of categories between Dieudonné modules and displays. A Dieudonné module is a finitely generated free W of K module with two endomorphisms, F, which is little f semilinear, V, which is little f inverse semilinear, F because K is perfect, little f is an isomorphism, so that little f inverse semilinearity makes sense, with the requirement that f composed with V and V composed with F are both equal to multiplication by P. So we can go, no, I didn't talk about this. Excuse me. So given a display, there is a unique morphism V natural from P to P upper 1, characterized by V natural of C times f of x equals P C tensor x, and V natural of C times F1 of y is C tensor y. This is for C in W of R, X in P, Y in Q. And both composites, F natural composed with V natural and V natural composed with F natural, are equal to multiplication by P. V natural can be extended. It goes from P to P upper 1. If we extend scalars for V natural using the ith iterative of Frobenius, we get a map from P upper I to P upper I plus 1. And these maps can all be composed. So we get a map V natural upper n, which is the iterate of these composites. And now we make the main initial definition. A display is nilpotent provided this V upper n is 0 modulo the ideal generated by IR and P times W of R. So in other words, it's as an endomorphism of a module over R modulo PR. And that should be true for some sufficiently big n. And we can go now to the next one. Excuse me? You'll see that of a nilpotent display. So the motivation comes, and the name comes from, there was a paper written in 1974 or 75, Peter Norman's thesis, or an outgrowth thereof, on studying and understanding or work of Mumford on deformations of abelian varieties and deformations of formal groups. And Norman looked at what are called displayed equations. And when I get to talking about the Cartier theory, that's where I can say a little more, try to say a little more about the motivation, the relation between Zink's theory of displays and Cartier's theory of classifying formal groups via typical curves. Okay, but let me try to come back to that. So, we can go to the, oh, no, excuse me, I want to, so an example, nilpotency for, if R equals the perfect field, then P sub m, that display is nilpotent, means V is nilpotent modulo P, which corresponds, depending upon whether one is looking in covariant or contravariant classical Dieudonné theory, but let's say covariant, to a p-divisible group being a formal, a connected p-divisible group. So if we go back to the Lubin-Tate formal group, the corresponding display is going to have P be the tensor product of the ring of integers of k over the p-adic integers with W of OK. So let me take a moment to say what the mapping is from ZP to W of OK. We have a natural mapping from ZP to OK because K is an extension of QP. But there's a mapping from ZP to W of ZP, which is characterized by the fact, in this case, that that ring homomorphism composed with the ghost components is the identity for each ghost component, little w sub n. And we'll come back to that more generally if we have a ring and an endomorphism lifting Frobenius, if we call the ring A, then there's always a mapping from A to W of A. This is the so-called Cartier map, which goes back to his 1972 seminar. So that's how W of K, OK, is a ZP algebra, and that's how the tensor product makes sense. Q is the kernel of the obvious mapping from this P to OK, namely the identity on OK and the W0 on the W of OK. F1 is easy to characterize by F1 of the uniformizer tensor 1 minus 1 tensor, this pi in brackets is the Teichmuller representative, that is the Witt vector given by pi, comma, 0, comma, 0, and so on. And the explicit formula for F is too complicated to write down here, and you see nothing from it, or I see nothing from it. So we can go to the next transparency. I'm going too fast. So I want to talk about base change for displays. If we have a ring homomorphism U, and we have a display over its source, R prime, we get a display over R, call it P, by, on the module is you extend scalars from W of R prime to W of R. The Q is, well, its definition is the kernel of the mapping from P to R tensor over R prime with P prime mod Q prime. This will be simply the scalar extension of Q prime if R prime to R is surjective, but in general it's not. The F is characterized by what's written there. It's the tensor product of little f and the original f on P prime. And the F1 is characterized in the way I write down. F1 applied to V of C tensor x is C tensor f, tensor x prime is C tensor f of x prime, and F1 of C tensor y prime is f of C tensor F1 of y prime. Okay, and I think we can now go to the next. Excuse me. So there's an elementary fact that is proven as an exercise in Bourbaki, algebra, chapitre 8, which is, in fact, I learned after being épuisé for many years. This is going to be republished in a completely new edition, and when I was told this by the Bourbaki secretary, my reaction was there was nothing wrong with the first edition, the only edition of this book from 1958. I think it's a marvelous book. So unless there's going to be the relation between the Brouwer group and étale cohomology, I don't see why they're reworking it, but that's Bourbaki's problem. So another reference for the result is in Bass's Algebraic K-theory, the big Benjamin book, chapter 3, I think, or perhaps chapter 2. It tells us when we can lift finitely generated projective modules. If we have a surjective homomorphism whose kernel is a nil ideal, or the ring is separated and complete in the topology defined by the kernel, then a finitely generated projective module can automatically be lifted. And by Nakayama, this is unique up to non-unique isomorphism. And a consequence, here there's I have to add something. If R prime is surjective, P is nilpotent in R, and the kernel of R prime to R is a nil ideal, or R prime, or the kernel is, R prime is separated and complete in the J-adic topology, then any display over R may be lifted to a display over R prime. And the display over R is nilpotent if and only if the lifted display is nilpotent. So we can go to the next one now. So I now review, this occurred implicitly this morning in Ching Li's talk, the definition of what a crystal is. So if we have a divided power thickening of a ring, that is surjective homomorphism where the kernel J is equipped with divided powers. So I might say, since divided powers were not really discussed in any detail this morning, divided powers first arose in the 1955 Seminaire Cartan on cohomology of, or homology of Eilenberg-MacLane spaces. This is where the notion first made its official appearance. And there are various things one can say about the divided power algebra associated to a module, and the fact that in an appropriate sense it is dual to the symmetric algebra associated to the module, but let me let that go and stick to crystals. The ideal generated by P in any ring automatically has divided powers, and one imposes frequently a compatibility condition that if we take an ideal J with divided powers and look at its intersection with P times the ring, the two divided power structures on that intersection should be the same divided power structure. This is the so-called compatibility condition. Now, the notion of a crystal on the ring R is the giving for each R algebra A and each divided power thickening A prime of a finitely generated projective A prime module, M sub pi. So this depends really on not only on the surjective ring homomorphism, but on the divided power structure. And if we alter the divided power structure, then these modules can have, in general, very little to do with one another. And what we require is that if we have a diagram of these divided power thickenings so that the mapping from A prime to A should commute with divided powers, it's a commutative diagram in which that mapping should commute with divided powers, we're to be given an isomorphism between the extension of M sub pi to a B prime module and M sub, I can't even read the Greek letter at this distance. What's the mapping for eta, M sub eta? And then there's a cocycle, a transitivity condition imposed, as is always the case when you're dealing with fibered categories. Okay, we can go to the next one, I think. So now we have a theorem, and I'm going to say something about it a little later when I go to the handwritten transparencies, how it's proved. So P is nilpotent in R. There's a functor which goes from nilpotent displays, not from all displays, but nilpotent displays, to crystals on R. And the functor takes values in the category of Dieudonné crystals. A crystal on a ring depends only upon the reduction of the ring modulo P, and if R has characteristic P, there's a mapping from the display P to its base change, P upper P, given by the mapping that I called earlier V natural, and a mapping in the other direction from the display upper P, the base change via Frobenius, to the original display P, induced by the F natural, and these are going to turn out to correspond to, the V natural will correspond to Frobenius on the associated P divisible formal group. The F natural will correspond to Verschiebung, but that's just, this interchange of the letters is just a fact of life. So a Dieudonné crystal is a crystal in which there are mappings given F and V, both composites being multiplication by P, mappings of crystals. There is also a functor from displays over R, all displays, to formal groups over R. And I'll describe this functor now. If we're given a display, and I'm going to view a formal group as a nilpotent R algebra, as a functor on nilpotent R algebras, set G upper 0 sub P of n to be the tensor product of W hat of n over W of R with P. W hat of n is those Witt vectors, entries in script n, almost all whose components are 0. W hat is, so to speak, the formal completion of W. And this is G0. And we take, now we can go to the next one. Want to look at G, I can't remember if I called it upper minus 1 or G upper 1, but we'll see in a moment. G minus 1 of n is the submodule generated by the V of C tensor x and the C tensor y, where C is in W hat of n, x is in P, y is in n. And there's an obvious mapping, F1 minus the inclusion, so to speak, given by these two formulas. You can read them, and there's no point in my reading them. The definition of the formal group associated to the display P as a functor on nilpotent algebras is that we take the co-kernel of this mapping from G minus 1 of n to G0 of n. And we can go to the next transparency, or next slide. There's a theorem that if we take, in fact, the first part of the theorem says that this is, in fact, a formal group in the sense defined, but more important for us today, if the display is nilpotent, then, in fact, this is a p-divisible formal group of finite height. And now I'm going to come back to this at much greater length tomorrow in the second talk. If we have a divided power thickening and assume the divided, I don't have to do that yet. We can take the so-called universal extension of the a p-divisible group. G prime is a p-divisible group over the ring A prime. It has a universal extension by a vector group. What this corresponds to, if we're working in characteristic 0, say over the complex numbers, or over any field of characteristic 0, in fact, over any base scheme whatsoever, is if I want to describe the universal extension of the dual of an abelian scheme. So I think of this as pick, the identity component of pick of the abelian scheme, and I can realize this as the sitting inside H1 with values in O star, or H1 beta with values in GM. I can think of this as the extensions, as was mentioned this morning, the Weber-Barsadi formula, that the dual abelian scheme is X1 of A with coefficients in GM, X1A comma GM. I can look at, so thinking of these elements as particular line bundles, I can look at line bundles equipped with an integrable connection, where I have a mapping from those to line bundles, forget the connection. And that map has kernel, which is given by the trivial line bundle, and the set of connections on the trivial line bundle is canonically identified with H0 of A with entries in omega 1, the cotangent space at the identity. And that sequence plays the role for or is the universal extension of the dual abelian scheme. So there is an extension of any p-divisible group by a vector group. In fact, the vector group is going to be the cotangent space at the identity. I write G star for what was written this morning as G upper T, the so-called Serre dual, the dual p-divisible group. And that extension is universal in the sense that given any extension of a p-divisible group by a quasi-coherent sheaf, there's a unique linear mapping from the omega to the quasi-coherent sheaf. So I remark that if one is in characteristic P, there are non-linear mappings between quasi-coherent modules. So linear is an important requirement. And that's the meaning of the universal extension. The Lie algebra of this E of G prime is up to canonical isomorphism independent of the choice of G prime. And I'll talk about why that's true tomorrow, but I just want to use that now. We can go to the next transparency. So we define the covariant crystalline Dieudonné functor. There are various definitions, but this is the initial one to be this Lie algebra, the tangent space at the identity. Since G is commutative, it's just traditional to denote it by Lie, but the bracket is trivial. And now there's a basic theorem of Zink, one of his main theorems in his asterisk paper. If we have a nilpotent display so that associated to it is a p-divisible group, Bt sub p, I should say the obvious thing, that Bt stands for Bossardi-Tate. Then there's a canonical isomorphism between the crystal that Zink associates to P, of which I'm going to talk a little more in a little while, and the crystalline Dieudonné functor associated to the corresponding Bt sub P. So we can go to the next one now. Thank you. And this is compatible with the Hodge filtration. So in the Hodge filtration, for the abelian variety, is H0 of omega 1 goes to H1 Durham, goes to H1 of OA. So now I come to a definition that a Nagata ring, so this is a definition one finds in the Matsumura book on commutative algebra. One finds it in Bourbaki, where it's a ring with the property that, first of all, it's Noetherian. Second of all, if we take any prime, any point in its spectrum, and any finite extension of the fraction field of R modulo P, the integral closure of R modulo P in L should be a finitely generated R modulo P module. So, any excellent ring, if you don't know what an excellent ring is, you can look in EGA chapter 4, paragraph 7, for maybe not an exhaustive study, but certainly some study of them. And if R mod P is essentially of finite type over a field, R is a Nagata ring. So there are lots of Nagata rings that arise in nature. So it means it's a localization of a ring of finite type. So we have a theorem. I would perhaps like to say something about its proof in a little while. If P is nilpotent in R, or more generally, if it's topologically nilpotent and R is separated and complete in a topology and a linear topology, and R is a Nagata ring, Bt is an equivalence of categories between nilpotent displays over R and p-divisible groups over R. This is a very p-divisible formal groups. This is a very, very strong theorem. And I'd like to make a comment about it now. One might say Cartier's theory gives over any commutative ring whatsoever. There's a Cartier theory which gives an equivalence of categories between formal groups and so-called reduced Cartier modules. And in case the ring is a Z localized at P module, this theory has, so to speak, decomposes, and the P component of it is the so-called theory of typical curves that will be talked about tomorrow in Ching Li's lecture, I believe. Although in the notes, the theory is outlined in the general case as well. Cartier gives an equivalence of categories. There's a weakness in Cartier's theory I want to make a comment about, namely that, so in general, I should say, the ring W of R is essentially never going to be a Noetherian ring. If R is of characteristic P and R is not perfect, then W of R is not going to be Noetherian. And this means for some purposes it's hard to do dévisage. The modules that Cartier associates to p-divisible formal groups in his theory, the module of typical curves, despite some statements made either explicitly or implicitly in published literature, tend not to be free when viewed as W of R modules. And, well, I should say, in the book of Falting's Chai, there's an error explicitly on page 361 approximately, where it's asserted that they are. And these are going to be free when regarded as W of R modules only if the p-divisible formal group is of multiplicative type. And, okay, and implicitly, maybe I should say that in the paper of Norman and Ott in the Annals, it's asserted that these are free as W of R modules, but it's not true. So that's a disadvantage. So I apologize to my two colleagues, but so one advantage of Zink's result from my perspective, and certainly from his perspective, is that the modules that one gets are much easier to handle than the modules in Cartier's theory. So we can go to the next transparency. So I want to talk about a generalization of the notion of displays. So far, the nilpotent displays have been related to p-divisible formal groups, but as was discussed in this morning's lectures, there are the general p-divisible groups, the ones which have étale quotients. So we fix an Artin local ring with perfect residue field. And if p equals 2, this is an unfortunate, at the moment, an unfortunate restriction. We have to assume that the ring has characteristic 2. Then, if the residue field is K, the projection from W of R to W of K has a canonical so-called Teichmuller section, and call that delta. We let W hat of R be the set of Witt vectors, coefficients in R, such that x minus delta of pi of x has almost all of its components 0. They all lie in W of the maximal ideal, but we want almost all of them to be 0. Then this ring W hat of R is a subring stable under F and V, and one can replace W of R by W hat of R in the definition of a display we obtain then the notion of a Dieudonné display. This is in Zink's paper on Dieudonné displays. But we can go to the next one. And Zink establishes for R, the Artinian local ring with perfect residue field, that Dieudonné displays, that category is equivalent to the category of all p-divisible groups over R. Now, I should say that with regard to that theorem, he doesn't directly describe a functor, but rather builds up this equivalence by taking a p-divisible group over the Artin local ring and viewing it as an extension of an étale quotient by a connected part, and the connected part is easy to handle. That's essentially the theory of the nilpotent Dieudonné displays. And to handle the étale quotient is also not difficult using some elementary Galois cohomology. And the extension part is a little delicate, but it's not so bad. But again, one doesn't see a direct, explicit definition of the functor in either direction. So now I want to talk about a result which has been, it's a generalization due to Zink of a result of Broglie, a very striking result of Broglie. So there's the problem of the so-called mysterious functor, which was raised by Grothendieck in his Nice International Congress talk, which is, so in the Chai-Ort notes, there's a discussion of the Tate conjecture and the p-adic analog of the Tate conjecture. The p-adic analog was Tate's theorem from the Driebergen conference book that p-divisible groups over a Noetherian normal scheme whose fraction field has characteristic 0 to p-divisible groups over the generic fiber, this is an equivalence of categories. Now, if p is invertible in the ring, then a p-divisible group is necessarily étale and just a representation of pi 1 of the Galois group in that case. So Tate's theorem was proven when the fraction field has characteristic 0, and for many years it was an open problem that in fact motivated part of the development of crystalline Dieudonné theory. Berthelot and I had hoped to solve this problem, but in fact it was solved by de Jong in paper in Inventiones in 1996, I think. But it at least certainly used the ideas coming from crystalline Dieudonné theory, so in a key way. I mean, in some sense, it's a question of if you have a horizontal section of the generic fiber of an F crystal, which has some f of it is p to some power times it, you want to know that in fact it extends over the whole base, but I don't want to go into that now. So I'm digressing too much. Broglie classified p-divisible groups over the ring of integers of any local field of characteristic, residue field of characteristic 3, greater than or equal to 3. Previously, this had been done by Grothendieck for ramification index strictly less than p minus 1, and Fontaine in his asterisk volume on p-divisible groups over local fields gave a different proof of Grothendieck's theorem. And Fontaine, of course, solved the problem of the mysterious functor. Broy's theorem has been greatly generalized by Zink, and I'll try to say something about this in a little while. If you take S, any finite flat W of K algebra, local, and he introduced a notion of windows, A windows, where A is some ring, and this is a refinement of the notion of Dieudonné displays. So, okay, I still have 35 minutes to go, and I want to turn to the handwritten transparencies now. Any questions? So first, let me begin by indicating, I mentioned this earlier, Grothendieck's proposal for a possible approach to classifying all formal groups. So he's looking at formal groups, say, over a field, perfect field of characteristic P, but not necessarily commutative. We certainly know since Dieudonné, more than 50 years ago, how to classify commutative formal groups. So we introduce Z, the center, and the derived subgroup, and we consider two homomorphisms. I'm sorry. What? Thank you. We consider the natural homomorphism from Z to G to modulo its commutator subgroup, and the homomorphism from the commutator subgroup to G modulo the center. These are both crossed modules, and I'll explain that notion in a moment. So a crossed module is the giving of a homomorphism between groups. G1 goes to G0. This is a notion introduced by J.H.C. Whitehead in the late 1940s in connection with simple homotopy type. And in addition to the homomorphism, there's to be an action of G0 on G1, say a left action, such that the homomorphism applied to the transform of little x belongs to G1, G belongs to G0, is given by the formula, the conjugate of d of x, conjugation by G of d of x. And then d of x acts on y by just conjugation. So these imply two things, that the kernel of the homomorphism is a central subgroup and the image is a normal subgroup. And now, if we have fix an abelian group A and an arbitrary group B plus an action of B on A, then isomorphism classes of crossed modules with G0 modulo the image of D being B and the kernel being A correspond bijectively to H3 of B with coefficients in A. This is a very good interpretation of geometric meaning, in a sense, geometric in the sense that this can be generalized to, as in Breen's work, Grue stacks or Grue categories. Okay, so what does this have to do with formal groups? So we had I'll have to go back to where it is, the two extensions. We have the extension, or Z goes to G modulo the commutator subgroup. These are both commutative groups, Z and G modulo the commutator subgroup. The commutator subgroup and G modulo its center are both completions of linear algebraic groups. This is an old result of Dieudonné. And Grothendieck's idea was we have ordinary Dieudonné theory, which enables us to classify all commutative formal groups. We have completions of linear groups, and linear groups have been studied greatly, so a great deal is known about them. And his idea was to look at the two crossed modules and say that the A and the B are the same, and try to use the homological classification, this H3 of B with coefficients in A, to obtain classifications of all formal groups. And as I said earlier, to the best of my knowledge, no one has made a serious attempt to pursue this. Okay, so I want to talk about how zinc associates the crystal to a nilpotent display. So if we take a divided power thickening and let J be the kernel of pi, the ghost components, Wn, can be divided morally by p to the n. Explicitly, one uses the formula I write down there using the divided power structure, and then one establishes an isomorphism between W of J and J to the bold n by using these divided ghost components, so in other words, using the divided power structure. And one looks inside J to the power n at those elements, the first, second, and so on, all later components are 0. And one takes the inverse image of this in W of J. And one obtains an ideal in this ring over A prime. One takes the inverse image of Q in P prime. So in other words, this is Q prime plus I sub A prime times P prime. Excuse me, I have written it correctly, and I misspoke with what I just said. And now the F1, which goes from Q prime to P prime, extends uniquely to a little f linear map from this Q prime hat to P prime, with the property that thinking of J as an ideal in W of A prime, F1 hat of J times P prime is equal to 0. So F1 goes from Q prime to P prime, and this is an extension of it to something larger, this Q prime hat. And if we have nilpotent displays P1 and P2 over R, and we have an R algebra A and a divided power thickening A prime to A, any morphism from P1 sub A to P2 sub A admits an unique lift if P1 prime and P2 prime are any two nilpotent displays on A prime. There's a unique mapping alpha prime from straight P prime 1 to straight P prime 2, such that the alpha prime lifts alpha and commutes with both the F and the extended F1. It's the fact that it commutes with the extended F1. If we just required commutation with F1, there could be more than the single alpha prime. So this is what will be used to define the crystal. So The value of the crystal is defined on this P prime modulo IA prime times P prime, and it is well defined because of what I just said on the preceding transparency. There's a canonical isomorphism between, if we have two liftings of a display P prime 1 and P prime 2, there's a canonical isomorphism between them. And this enables one, in fact, to define a so-called Witt crystal, but one reduces the value of the Witt crystal would be the P prime itself, which is a W of A prime module, but one reduces it to get the crystal denoted by D. So now I want to talk about the relation with Cartier's theory. So I'll first have to tell you briefly what Cartier's theory is. So we take this functor W of hat, W hat. This associates to any nilpotent algebra the Witt vectors with entries in that nilpotent algebra, almost all of which are 0. And one looks at this as a functor on nilpotent algebras. One has its endomorphism ring, and one takes the opposite of that endomorphism ring. And if we have a formal group over the ring R, by definition, the Cartier module, the module of typical curves, the homomorphisms from W hat to G. This is a left Cartier. C sub R is the Cartier ring associated to the ring R, and it has the following property. There's our endomorphisms V and F of W hat. V corresponds to Frobenius on W hat. F corresponds to Verschiebung on W hat. This perversity is because the Cartier ring is the opposite of the endomorphism ring, but it induces an endomorphism on this M of G, V, which is injective. M is separated and complete in the V-adic topology, and M modulo Vm is a finitely generated projective R module. These are the so-called reduced Cartier modules, and Cartier's theorem says that there's an equivalence of categories between formal groups over the ring R and reduced Cartier modules. So I want to now describe zinc associates to any display a formal group. I want to describe in terms of the display what its associated Cartier module is. So I should say W of R maps naturally to certainly W of R sits inside the ring endomorphisms of W hat, or sits inside the endomorphisms of W hat as an abelian group valued functor. So the tensor product of the Cartier ring over W of R with P makes sense, and one takes the quotient of this by the elements generated. So this is a C of R module, F tensor X minus 1 tensor F of X, and V tensor F1 of Y minus 1 tensor Y, for X belonging to P and Y belonging to Q. And this is the Cartier module associated to BT of P. So it's a very explicit description, and it's used sometimes explicitly. So now I want to talk I'll talk more tomorrow, the deformation result. So if we fix a local field of characteristic 0 with perfect residue field, and we have a p-divisible group, we can let D of G sub k be the covariant Dieudonné module of its special fiber, and take L sub G to be the translation invariant differentials on the dual p-divisible group. Grothendieck's theorem, which I mentioned earlier, says that if E is strictly less than p minus 1, then the func that G goes to the Dieudonné module together with L of G is an equivalence of categories from P divisible groups over OK to filtered Dieudonné modules over OK. And the same result holds true if one looks at P divisible groups up to isogeny over OK and filtered crystals, Fi isocrystals, without restriction on the ramification index. And as I said earlier, Fontaine proves this in the asterisk. So here I want to talk about Zink's generalization of Breuil's extension. So we take a ring R such that P is nilpotent in R. A frame for R is the giving of a triple A, J, sigma, where A is a flat it's a ZP algebra, flat as a ZP module, separated and complete in the p-adic topology. Pi is an epimorphism on, or a surjection better, onto R. And the ideal J is equipped with divided powers, and sigma is a lifting of Frobenius. Now there's a definition of what Zink calls a Dieudonné A window for R. It's a finitely generated projective A module. By the way, I should perhaps give an example. If R is a reduced ring, then W of R can be taken to be A. A Dieudonné A window for R is a finitely generated projective A module, a submodule M1 containing J times M, a semilinear mapping phi from sigma semilinear, sigma is this lifting of Frobenius, from M to itself, such that M modulo M1 is a projective R module, and phi of M1 is contained in P times M, and M should be generated by phi of M union phi, since the module is torsion free, we can divide, and phi of M1 is contained in P times M. It makes sense to talk about phi over P applied to M1. So this is the definition of a Dieudonné A window. And then there's a unique mapping psi with the property that it goes from M to the scalar extension via sigma. Psi applied to phi of M should be P tensor M. And the Dieudonné window is called an A window if there exists an N such that psi of M is contained in J psi iterated N times. This is analogous to the V sharp upper N, V natural upper N should be nilpotent modulo P. This is the analog of that. So this is, so to speak, the nilpotent condition in the definition of a nilpotent display. This is the analog of that. And now we go a little further. So we have this divided ghost component isomorphism from W of J to the N. And inside the countable product of J's, we can take the countable direct sum and take its inverse image, which we'll denote by W tilde of J. And then W of A should be the subring generated by W tilde of J and W hat of A, where W hat of A has the same meaning that it did in the discussion of Dieudonné displays. So the frame is called a Dieudonné frame for R if we have the Cartier mapping. So this delta map is characterized by the following property, that the nth ghost component composed with delta, which is a mapping from A to itself, should be sigma to the nth power for all n. And the requirement is that this mapping should factor through the subring W tilde of A. So we now take S to be a local W of K algebra, which is flat, in other words, it's p-torsion free. And we present it as a quotient of a polynomial ring in such a way that the variables are mapped to elements in the maximal ideal of S. And then we take the divided power envelope of this ideal. There's a universal way, if we have any ideal in any ring, one can, in a universal way, add divided powers to it. That is, get an algebra if the ring is, well, let me change notation, because call B this polynomial ring. So if I have a ring B and ideal I, there's a B algebra, dp of I, with the property that it is universal for mappings from B to rings C equipped with divided power ideals such that I is mapped to the divided power ideal. That's the so-called divided power envelope. And we take the divided power envelope, and in general there's going to be lots of p-torsion in it. It will be p-torsion free if S is a complete intersection, but otherwise it's going to, in general, have p-torsion. But we kill the p-torsion and then call that ring A0. We take the p-adic completion of that, call that ring A. This is going to be the frame. It's a frame for S, and for each n, at least one, it is a S mod p to the n is going to be a Dieudonné frame for, excuse me, it's going to be a Dieudonné frame for S modulo p to the n. Okay, so Zink's theorem, generalizing Broy's, generalizing Grothendieck's, is the following. There's an equivalence of categories between Dieudonné A windows for the frame A goes to S via this pi, and p-divisible groups over S. The p-divisible formal groups over S correspond to the A windows relative to S modulo p. Okay, so that's Zink's generalization of Broglie. I want to end, I think, a little early today, although I can certainly begin. There's plenty to say tomorrow. I want to describe the Tate module associated to a BT of P for P in nilpotent display. So the Tate module was defined earlier in Franz's lecture for any p-divisible group. So we take R, a normal local ring, fraction field of characteristic 0, residue field of characteristic P, not necessarily perfect residue field. And we fix an algebraic closure of the fraction field of R. And if we have a finite extension of that field, the fraction field K, we define W hat of the maximal ideal of the ring of integers to be the projective limit of the W hat of the maximal ideal modulo P to the n times the maximal ideal. And then W hat of the maximal ideal of the integral closure of R in K bar is by definition the inductive limit of these W hats of M sub E, and W bar of this maximal ideal of the ring of integers of the algebraic closure will be by definition the p-adic completion of this W hat of the maximal ideal of the ring of integers. And we denote by M bar the p-adic completion of the maximal ideal of R. So in classical notation, if K was equal to QP, R was equal to ZP, we'd be talking about the maximal ideal in O of C sub P, where C sub P is the completion of the algebraic closure of QP, a field which is known to itself be algebraically closed and whose Galois cohomology enters in an essential way in the proof of the Tate theorem that I mentioned earlier on restriction to the generic fiber being fully faithful, and enters into the work of Shankar-Sen and Axe, and certainly in Fontaine's theory, Colmez's theory, it enters all the time. So this M bar is a known object. Okay, I want to describe now the Tate module of BT of P in terms of this notation. Here's the notation. So G0 bar of sub P, for P the nilpotent display, is going to be this W bar, the p-adic completion of the W hat of the MR bar. So these are, there are two different topologies going on. So the W hat of MR bar consists of Witt vectors with entries in MR bar, which almost all the components tend to zero p-adically. We tensor over W of R the underlying module of the display. G1, so P mod Q has the same meaning. M bar has the meaning, the completion of M of R bar. And we take G minus 1 to be the kernel of the natural mapping from the upper line to M bar tensor P modulo Q. And there's an F1 minus the inclusion, again, in this context, which is obtained from the F1 minus the inclusion by taking p-adic completion. And the theorem says that the Tate module of the p-divisible formal group associated to the nilpotent display is explicitly given in this way. The Galois group of K bar over K acts on every term in sight, and this is a Galois, I mean, it would have no interest unless it was Galois equivariant isomorphism. So, in Yuri's office, there are the displays for tomorrow's talk. Maybe I can write on the blackboard for 5 minutes and try to say something about how zinc proves the theorem, the equivalence of categories theorem, when we have the Nagata ring. And I'll just try to give maybe we have to turn, yeah, thank you. So the theorem said that if R is a Nagata ring, then BT going from nilpotent displays over R to p-divisible formal groups over R. This is an equivalence of categories. So the first step is that, and well, let's assume, one can pass to the limit. If R is separated and complete in the p-adic topology, then p divisible groups over R is equivalent to the projective limit in the categorical sense of p divisible groups over R mod p to the n. So there's no, and similarly for nilpotent displays, there's no loss in generality in assuming p is nilpotent in R. And the proof proceeds in small steps. The first step is R equals K, a field of characteristic P. And this is handled in the following way. One takes capital K to be the perfect closure. And the theorem, so let me first say, the hard part of the proof is to show essential surjectivity. It is known if we have any ring with P nilpotent and its nil radical finitely generated, then BT is fully faithful. And since a Nagata ring is by definition Noetherian, its nil radical is finitely generated. So we know, so to speak, it's a theorem of zinc, but we know, in quotes, for free, that this functor is fully faithful. The hard part is to show it is essentially surjective. So I give myself G over K, little k, a P divisible formal group, and I want to show that it is isomorphic to BT sub P for P in nilpotent display. So we first pass to the perfect closure, and we regard the group over capital K, and by classical Dieudonné theory, we know there exists, say, P prime, a display over capital K such that BT of P prime is isomorphic to GK, and we fix such an isomorphism. Then one looks at this tensor product. This is a ring with loads of nilpotents, unless little k is a perfect field. And we want to look at C equals, this is not for Cartier, this is for Cohen ring for little k. So this is a complete discrete valuation ring, maximal ideal generated by P residue field equal to little k, characterized up to non-unique isomorphism. And there's always a map, again, lifting the inclusion of little k and capital K of C to the Witt vectors of the perfect closure. This is, again, not well defined, but we make such a choice. And we then look at, say, the ring A, which is W of K tensor over C with W of K. This is a ring which is P torsion free and whose reduction modulo P is this ring. Using the fact that this ring is P torsion free, one can show that the functor BT for this ring is fully faithful, even though the nil radical of this ring is not going to be finitely generated at all unless little k is perfect. But using the fact that this ring is P torsion free, one shows that BT for this awful ring is fully faithful. So that enables us to say that this P prime, the display over capital K, has descent data. That is, when we pull P prime back to it in the two ways to W of this awful ring, there's an isomorphism between them satisfying the co-cycle condition by the full faithfulness of Bt over this ring, because the G coming from little k, this p-divisible group has canonical descent data. Okay, now Zink proves a theorem, a descent theorem for displays and for nilpotent displays, that if R to R prime is faithfully flat, then displays over R prime equipped with descent data in the obvious sense are equivalent to the displays over R, and the same is true for nilpotent displays. So knowing that this P prime, so the mapping from little k into capital K is certainly faithfully flat, and knowing that P prime has descent data, P prime descends to a nilpotent display P, and then it's easy to see that Bt of the descended display will have to be the original G. So this is the proof when little k is a field. The next part of the proof is when we have an Artin local ring. So in this case, the proof uses the comparison between the crystal associated to, so let me write it, so D sub P, where P is the nilpotent display, and the covariant D lower star of Bt sub P. The fact that there's a canonical isomorphism between these crystals compatible with the Hodge filtration, and the deformation theory for p-divisible groups that was discussed by Jing Li this morning, the so-called growth and deep messing theorem, to say that, or to deduce that, if we have G over R, the p-divisible formal group with special fiber G sub k, then, and this one we know that this is equal to, say, Bt of some display P over K. Then, using this theorem, and I mean, since R, there's no question of divided powers, but since its ideal is nilpotent, one filters it by square zero ideals, imposes trivial and therefore nilpotent divided powers on them, and deduces that given a p-divisible group over an Artin ring, lifting a p-divisible group associated with the display, there is a display P over R, nilpotent display, such that Bt sub P is isomorphic to G. So this comes from this and the deformation theory. So this handles the case of essential surjectivity in the case of an Artin local ring. What about a complete Noetherian local ring? This is an interesting case. So R equals a complete Noetherian local ring. So I should remark that the Artin ring case, or the method that is dividing through by the nil radical, enables us to assume that this ring is reduced. We may assume R is reduced. And you'll see there's an interesting way in which this enters. So we know the theorem, essential surjectivity, for R modulo m to the n, where m is the maximal ideal for all n. So this gives us a so if we have a p-divisible group G over the complete Noetherian local ring, and we have Gn, its reduction modulo the maximal ideal to the n, we get a family of nilpotent displays Pn such that Bt of Pn equals Gn, And what we would like to know, what requires proof, is that if we consider the category of all displays over R and all displays over the R modulo m to the n's, there's an equivalence of categories between projective systems of PNs and displays over R. But what we would like to know in this case is that this, in quotes, projective limit of the PNs, the corresponding display over R, is in fact a nilpotent display. That requires proof, and in fact, the proof relies on the description given earlier of the Cartier module associated to Bt of P, where P is an arbitrary, not necessarily nilpotent display, and the fact that R is reduced is to enable us to embed R into a big product of algebraically closed fields. Say the algebraic closure of the fraction field of R modulo P, where P runs through the prime ideals. And that enables us to finally reduce to the case when we're dealing with an algebraically closed field, and then over an algebraically closed field, the structure of p-divisible groups is very simple to understand. The structure of Cartier modules is relatively simple to understand, and this enables one to handle the case of an algebraically closed field. So let me try to, if we can raise this screen somehow, I'll use the blackboard here. I'm almost done. So I apologize for not following the German tradition of erasing with the water. But in the interest of saving a little time and finishing the proof, let me go on. So now let's take a Nagata local ring. Call it R, which again we may assume is reduced by the same reason discussed, and we take R hat its completion. Then we can look at R hat tensor R hat over R. This is in general certainly not going to be a Noetherian ring anymore, but using the fact that R is a Nagata ring, it's a theorem, Bourbaki, algèbre commutative, chapitre 9, paragraph 4, and it's a theorem due to Zariski and Nagata, it's not due to Bourbaki, that both R hat and this tensor product are both reduced rings. So, using the fact that they are reduced rings, even though this is no longer Noetherian, so that its nil radical need not be, if we had a general ring, nil radical need not be nilpotent, so we wouldn't have full faithfulness. Since this is a reduced ring, its nil radical is 0, and we have full faithfulness over this ring. So if we have, again, G over R, and let me write G sub R hat for its extension to R hat, and we know we have a, let me write a P sub R hat with BT of this being equal to G sub R hat, then again, the full faithfulness implies that there is descent, and this P sub r hat descends to a nilpotent display on R, and again we get, for the descended display P, Bt of P equals G. Equals, of course, means an isomorphism giving by extension of scale is this isomorphism. Okay, so now the last case is the general Nagata ring. And here one takes R, maps it to the product of all its localizations, that's all its maximal ideals. And this is, of course, injective. And one, beginning with the G over R, let's take, so to speak, the product of the G with obvious notation, the G sub m's. That is the p-divisible formal group we get by extension of scalars. And to give a p-divisible formal group over such a product of rings is equivalent to giving 1 over each factor. To give a display over a product of rings is the equivalent to giving 1 over each factor. This is, in both cases, because of the fact that to give a finitely generated module over a product of rings is the same as giving a finitely generated module over each factor, at least provided the rank of the module is constant. And by localizing on the original Nagata ring, we can assume that the height of the p-divisible group G is a constant function. Then the fact that if we have a display over the product of rings, which when we project onto each factor is a nilpotent display, that it is in fact a nilpotent display, that in other words, so to speak, the power of this mapping V natural to the n can be taken independent of the maximal ideal. This is because essentially, just as in linear algebra, if we have a module of some, or say a vector space of some fixed dimension and a nilpotent endomorphism, the index of nilpotency is determined or is bounded above by the dimension of the space. So that enables us to show if we have a display over the product, each term of which is nilpotent, then it itself is nilpotent. So that gives us, for this product, a nilpotent display. I don't know how to, let me write it as a product of P sub m's, which is isomorphic to this product of the. So I apologize, I won't go near this metal again. We learned our lesson, and I should have not made that mistake twice, but I won't do it again. Okay, so again, what does one want to do? One wants to descend this display down from this product to here. So one attempts the same thing. One takes the product, one maps it to the product of Q sub R sub m, where Q denotes the total ring of fractions of the local ring, and one tenses this with itself over the product, and now what one wants to show is that we can assume that that ring is reduced, since R is reduced, and this is, let me get out the, if I can find it, it's here someplace, the written Bourbaki talk. I hope I haven't, no? I have it. So I'll just read to you what I wrote, and then I'll close with apologies for running over. So I'm going to introduce some notation, which I should have introduced earlier had I been looking at this. So R prime equals the product. So we would like to show that this R prime tensor over R with R prime is reduced. That's what we need to show. So R prime is faithfully flat over R so that R prime tensor with itself over R embeds into the total ring of quotients tensor over the total ring of quotients of R with the total ring of quotients of R prime. So this is simply because R prime is faithfully flat over R. R is Noetherian and reduced, so R, the total ring of quotients, is a finite product of the total ring of quotients of R modulo its minimal prime ideals. That is the fraction fields. And this enables one to show that this tensor product is a product of this tensor product is equal to, I'm sorry, so it is equal to this finite product. And finally, this reduces us to the case where we have the product of the we take this ring for each minimal prime ideal, tensor it with itself over the fraction field of R modulo the minimal prime ideal. And that last thing enables us to say if we have any field K whatsoever and any set I whatsoever, K to the I tensor over K with K to the I, this should be reduced. That's the final reduction, and this is well known. A countable product of fields is a separable algebra over that field. So that's elementary algebra in Bourbaki, for example. And that completes the proof of Zink's equivalence theorem. And I thank you for your indulgence.